Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I hope that you are all doing very, very well and having a wonderful week. And thank you for joining in on the webinar today. I'm excited to present to you all, and we're going to go over some great content today, getting back to the basics of AFT software. I'm going to be demonstrating using AFT Fathom, but the same features that I'm showing here in AFT Fathom are also available in AFT Impulse and AFT Arrow. And so there's a lot of good crossover there that you'll be able to take advantage of in other software tools that we provide in today's webinar. And we will also be getting into some more advanced stuff too as I go along in the example. And so before I begin, I just wanted to go over really quick where you can find some more information about the software tools that we do have available. Our website is aft.com. And under aft.com, if you go to the products menu and to the AFT software overview page, this is where you can find some more information about our software. And so many of you are familiar. We have AFT Fathom, which is for liquid piping systems and using incompressible flow methods. AFT Arrow models compressible flow in gas piping systems, while AFT Impulse models water hammer for liquid piping systems. And each software product has a number of outstanding add-on modules that can extend your usage and capabilities. And I would highly recommend checking them out sometime because they can be very helpful. And today, when I get into my example, I will be showing a little bit of what the goal seeking control module can do for AFT Fathom. Note that AFT Arrow also has a goal seeking control module, so the concept would be exactly the same on how you'd be able to use that feature. So you'll be able to see that today. And let's go ahead and get into it. So here is AFT Fathom that I'm sure many of you are familiar with. And again, this is a back to basics webinar. So I am going to cover some of the basics things that a lot of you know, but it will quickly accelerate. So don't worry. If you are brand new to the software and this is the first time that you've opened it, or maybe it's the first time in a long time, maybe you used the previous version a long time ago, and you're just trying to get back up with what you're doing, the first thing that you want to pay attention to is the red status light in the bottom right hand corner of the software interface. The whole goal is to make that red status light turn green. Once it turns green, you can run your model and get results. So that's the first part of the first step of the yellow brick road. So what I want you to do is click on the red status light, so that way it'll bring up the checklist of items that need to be completed for you to run your model. The first checklist item is to specify solution control, and this is the default tolerances that will dictate if you have a converged solution. I highly recommend just leaving these values as they are because the default solution control tolerances will solve about 98% of the cases for you. So rarely will you ever need to go in and muck around with the solution control tolerances. And when you keep them as they are, you get your first screen check mark for free. Second item on the checklist is the specify system properties. This is where you define your fluid data. And as you can see, the default fluid is to do a user specify fluid. And here comes the next piece of the yellow brick road, is to pay attention to the blue highlighting that you see in the windows. Wherever you see blue highlighting, that indicates required input. So as long as you define your density and your dynamic viscosity, you've completely defined your fluid data and you would be able to run your model and do the hydraulic calculations. I highly recommend also specifying a vapor pressure. Even though it's optional, it allows you to do MPSH-A calculations on your pumps, and it will compare against your system static pressure to identify if you are cavitating anywhere in your system. So be sure that you specify a vapor pressure as well. In today's webinar, I'm not going to go through all the different fluid modeling options that you can work with in the system properties window. I'll leave that to you to explore on your own. What I'm going to model today is one of the AFT standard fluids, and yep, you guessed it, I'm modeling water. Water at 1 atmosphere. Simply click the Add to Model button and then type in a temperature for the given range. Click Calculate Properties, and that's all there is to it. When you use the Constant Fluid Properties option, it's going to use these values in every pipe throughout your model. And so that's as far as I'm going to talk about in the System Properties window today. Again, I leave you to explore this on your own. So once you get the values here for your properties, you can change the units if you want. Just click OK, and you get your second green check mark. Now, this is where the fun begins, is defining all your pipes and junctions. And in order to define your pipes and junctions, there has to be pipes and junctions. So when you go to build your model, there's a few different ways to do this. First off, if you happen to have any standard neutral file formats, like a piping component file, which usually comes from isometric drawings from CAD software, or a Caesar 2 neutral file, or GIS shape files, or EPANET files. These are the 4 neutral file formats that we can import into the software, and it will build the model of the piping system for you so that you don't have to build it from scratch. It'll also define basic information like pipe size, length, as well as elevation information for your junctions. So this is really helpful in saving you some time if you have any of these neutral file formats. And again, where you find this option is in the File menu, and then Import Piping Layout, and then you're off to the races. I'm not going to demonstrate this today. I just wanted to show you where you can find that. Today, I'm going to demonstrate building a very simple system from scratch, but you're going to see a lot of features that will help make it a lot more efficient for you as you build your system. Give me 1 second here. Okay, excuse me. All right, so to help me build my system, I'm going to click on the Arrange menu, and I'm going to turn on the grid. There's different grids that you can work with. This is the standard 2-dimensional grid that we've had available for a long time. We also have available a isometric grid, which allows you to build your model to make it look isometric in a lot easier of a fashion. So if you want to build your model isometrically, this is a really helpful way to be able to do it. Today, I'm just keeping it easy. I'm going to stick with my 2-dimensional free-form grid, and that's all there is to it. So now, in order to build your model, you're simply going to use a mixture of the various pipes and junctions that we have in the toolbox on the left-hand side. And so this is the pipe drawing tool. This is an annotation tool, which is a glorified text box. We use the word junction as a common term for any of these components that are not a pipe drawing tool or an annotation. So that's what we mean by the word junction. It can mean any of those different components. So it's just a simple drag and drop interface. I'm going to drag and drop starting with a reservoir junction. That's going to set up my supply boundary pressure, and I'm going to put it right there. Next, I'm going to use this screen to model a filter, and so I was just counting the squares so that I can put them nice and far apart from each other. Followed by that, I've got my pump, and then I'm going to put a general component, which is going to model either some process unit or a internal part of the system that has a whole bunch of piping that I don't know anything about. I don't have drawings, I don't have any details. I could lump all of the hydraulic losses into a single component, and I'm going to show you how to do that here in a little bit. Lastly, I'm going to lay out my discharge reservoir. I'm going to put it right there, and then I'll zoom to fit. If you don't know where the zoom to fit button is, it is right here, and that way you can zoom out to fit all of your system inside. Now, in order to connect the dots, you simply double click on the pipe drawing tool and click and drag your mouse from the middle of one junction to the middle of the next. Nice and easy. And there we go. So now that I'm done, hit the escape button to turn off the pipe drawing tool. That way you don't have a bunch of extra little pipes strewn about throughout your workspace. Now I'm going to go to the tools menu, and under the user options, this is where you can change any of the different preferences inside the software. And I'm going to change my font size to make it larger and easier to see. There we go. So everything is size 16. Now, this is the next step of the next piece of the yellow brick road is to click on the link that says define all pipes and junctions. It does two things. One, it automatically clicks it turns on the light bulb, and this is going to highlight the label for a pipe or a junction in red. That is a visual indicator that those objects are not fully defined. So that's really helpful for being able to quickly spot where you might be missing a diameter somewhere, perhaps. The other thing that it does is it brings out the list of undefined objects panel, and this catalogs all of the pipes as well as all of the junctions that are missing some piece of input information. And this is a really helpful tool because when you click on any of these, it's going to move your system to the location of where that object is. It selects it on the workspace for you, and then it tells you exactly which pieces of input information are missing. That way you are never left guessing what you have to specify. All right, so now that we have this turned on, I'm going to start by defining my junctions first. So in order to define your junctions or your pipes, you just double click on stuff. So I'm going to double click on the supply reservoir, and again, follow the blue highlighting. Wherever you see blue highlighting, that's required input. Now, the nice thing that you notice here is for liquid surface pressure and the pipe depth, we already have common values that you might be using most of the time specified. That way it can save you some input time. So this is assuming that your reservoirs are open to atmospheric pressure. That way it's just 0 psig, maybe one less thing that you have to worry about specifying. Now, the pipe elevation is more helpful to use, in my opinion, because if you want to do different scenarios where you're changing the liquid surface level, you don't want the pipe connection to change either. So when you use pipe elevation instead of pipe depth, the elevation is going to fix the location of where your pipe is connected. Now, a couple of things I want to note on reservoir junctions. The reservoir junction represents a infinite source or sink of fluid that will fix a pressure at the connected pipe. Therefore, this liquid surface level is not going to change unless you change it manually. It's an infinite body of fluid. So if you want to be able to show how your liquid surface level changes during a simulation, maybe you have different pumps kicking on and off, maybe this is a wet well and you want to be able to see how you are filling up your pit and draining it, then that's going to be a really helpful application for the extended time simulation module. So let me take a quick sidestep here. This is where you can turn on the add-on modules right down here. And so if I was to turn on the XTS module for extended time simulation, this allows me to do some transient modeling with AFT Fathom. So now when I open up my reservoir window, you can see that there are two new options available to me to model finite tanks. So if I model a finite tank here, I can specify the actual tank geometry. And when you do it in this fashion, you will be able to actually see your liquid surface level change during a transient simulation period as your pumps are kicking on and off. So XTS is really helpful for extending the capabilities of Fathom to do some transient modeling. Now, for today's webinar, I'm not going to get into using the XTS module. I'm going to turn this off. If you want to learn more about transient modeling, I would highly recommend watching one of our previous webinars. So if you go to the Learning Center under Webinars and then Webinar Library, this is where you can fill out the information with your contact details, and then you'll be able to access all of our previously recorded webinars for free. And there's a really important webinar in here, and if you scroll down, it's going to be more near the bottom area, and it's called "What Does Transient Analysis Mean?" The reason why I titled it that in the webinar is because transient analysis is too general of a term, and you could either use Fathom with the XTS module or AFT Impulse, depending upon the transient situation that you're trying to model. And this is an excellent webinar that will demonstrate exactly what those differences are and when you would use the appropriate tool. So watch that webinar and it will give you some more information about transient modeling with AFT software. All right, back into Fathom here. So in today's webinar, this is just going to be an infinite reservoir, and I'm going to specify a liquid surface elevation of 10 feet. Now, even though it's infinite, I can still use this to determine the liquid level of my supply tank. So that's still perfectly fine. I can call this supply tank if I want to. You just need to make sure you keep it straight in your head that this is an infinite reservoir. And I'm going to connect the pipe elevation at the bottom, and that way it will set the piping to a 0-foot elevation. The liquid surface level that I've specified is just a guess. I don't actually know what the liquid surface elevation is, and so I'm going to show you how we're going to change that to determine what the supply tank liquid level should be shortly. So there's our supply tank. The label turns black when that object is fully defined. So now that's fully specified, let's move on to the filter. Here, as you can see by the blue highlighting, the minimum input for junctions is elevation data. So when you specify elevation data for your junctions, that is one way that your piping will pick up the elevation change throughout your system. Now, there are some standard screen models that we've built into the software for you, but today I'm going to do user specified with a resistance curve. The reason why is because my filter manufacturer told me that at my design flow rate of 500 gallons per minute, I have a pressure loss of 5 psi. So when you're only given a single data point like this from your manufacturer and you don't have any other information, what do? Well, if you were to try and click on the Generate Curve Fit Now button, it's going to throw up a message that's saying you only entered one data point. would you like to fill the data points to generate a quadratic curve fit? And so basically this message is asking, do you want to click this button right here that says fill as quadratic? I'm going to do it incorrectly first. So here I'm going to click no. And this is what it does. It generates a horizontal resistance curve that represents the same pressure loss at all flow rates. And this is just completely incorrect. The other issue is that my design flow is 500 gallons per minute. If the system flow actually is much lower, maybe 50 gallons per minute, this would represent a infinite resistance in that case, and this very well could cause convergence issues. The reason why I stress this really heavily is because this is a very common mistake that we see in many user models, is either they will only specify a single data point, or they will simply define a single A constant. So this is not good, don't do this. So when you only have one data point from your manufacturer, that's where you can click on the fill as quadratic button, and this will generate 2 additional data points for you. The first data point is at the origin, third data point is extrapolated along a quadratic. So when you don't have any other information, this is going to generate a much more realistic loss across this component for you. So that's a much better resistance curve that you'll want to model. And there it is, and that's going to capture the losses across that component. I'll click OK, and now that's fully defined. Next up is my pump. So one of the default options is that Fathom, Arrow, and Impulse will remember the most recently used elevation for you. And that option can be configured in the user options window in the tools menu. So if you want to make that be a different value, you certainly can, but otherwise it'll use the most recently specified elevation, potentially saving you a little bit of time. Now, I can model centrifugal pumps as well as positive displacement pumps. For a PD pump, it's just going to be a fixed flow rate, but you have the added capability of being able to specify to calculate the acceleration head via the Hydraulic Institute standards. So if you're dealing with positive displacement pumps, then be sure to account for those extra calculations. One other quick side step is if you're using AFT Impulse for doing water hammer modeling, the positive displacement pump capabilities are a lot more sophisticated, and you can really capture the pulsating behavior of a positive displacement pump with AFT Impulse. So if that's your situation and you want to get a better handle on what's going on, then be sure to check that out. All right, in my model today, I'm going to model a centrifugal pump, but the issue is I do not yet have a pump curve. All you need is some basic data for flow and pump head, and that's all you need to define your pump curve. You don't have to have thousands of data points to accurately model a pump curve. You just need a few good data points. You can also put in your MPSH and your efficiency or power values, and then you'll be able to generate your curve. But because I don't yet have a pump curve, I need to size my pump. So I'm going to choose the sizing option, and I'm just going to specify my design flow rate of 500 gallons per minute. And we'll click OK, and there we go. So now that's fully defined. All right. Now this right here is going to be an internal process system. I'm going to call it internal process system number 1. And just like how I mentioned, you can model a resistance curve to model the effects of a physical component like a filter or maybe even a heat exchanger, or you can use it to model the hydraulic behavior of an internal part of your system. And so I want to take you to a quick case study here under the Learning Center and then case studies. If you were to filter by industry for automotive applications, this is a really neat case study where the Chrysler plant that makes Chrysler cars in Michigan in the United States, they built a model which allowed them to save $194,000 per year in energy costs. Also, they were awarded a $200,000 rebate from their local electric utility. And I want to show you their system. It's not that complicated. There it is. So as you can see here, the reason why I mention this is because you could have a very, very simple model just like this and still accomplish big things. And that's exactly what they did. They had a whole system with a bunch of piping and components that they didn't really have a lot of information on, and they just lumped all of that hydraulic loss behavior into this single component right here with a resistance curve. And so that's a really useful way to keep your system nice and simple. So that's what I'm doing with this here in this resistance curve. And I'm going to specify just one data point, and I'm going to click on the fills quadratic button. I am pretending that these data points are actually real measured data points. So I don't have thousands of data points on hand to enter in. And so I'm just pretending that that's my actual measured data for that whole system. And I'm simply representing that with a resistance curve. So similar to the filter, but instead of modeling a component, this models a whole internal system. All right. Now the last junction here is going to be the reservoir junction on the discharge end. And this is going to be a liquid surface elevation of 200 feet. The pipe elevation is also going to be at 200 feet. And I'll click OK. And now my discharge reservoir is specified. Time to move on to the pipes. In order to open up a pipe property window, you can just double click on it. But if you're like me, I'm not always that great at being able to double click right on the pipe itself. So here's a couple of tips with regard to selecting things on your workspace. If you were to take your mouse and click and drag from left to right, you'll see how that black box appears. The black box is going to select any object that is only completely within the box. So as you can see, it only selects the filter. Now, if I click and drag from right to left, the box is yellow. This is going to select anything completely in the box or crossing the boundaries of the box. So notice how it grabbed the two additional pipes for me. So a lot of times when I go and I try to select pipes, I'll just click and drag a little bit over that pipe like this and select it, and then hit enter on my keyboard, and that opens it up a little bit easier for me. All right. Minimum input is inner diameter, length, and friction model. If you choose user specified, you can do absolute roughness, Hazen-Williams, explicit friction factor, etc. Or you can choose from one of our pre-built pipe material databases where you can select your nominal size and schedule, and it'll do the inner diameter from the database. And if you want to change the friction model to something other than standard, which we only use absolute roughness from AFT, if you want to do something different, just choose user specified, and there you go. Now, I'm not going to define my pipes one at a time. This is where I'm going to demonstrate a really important feature that you want to make sure that you know how to use, called global editing. So all of my pipes are going to be the same material, nominal size, and schedule, and I'm going to edit their input information at the same time. Here's how you do that. You go to the edit menu and then go down to global pipe edit. And I'm going to click on all to select all the boxes in the list for all of the pipes. Next thing is I'm going to click on select pipe data. Now, this is the same window that we just saw before for entering piping information. So I'm going to specify steel material. It's going to be a nominal size of 4 inches in diameter, and it's going to be standard friction. But here's the thing. The length field is highlighted in blue, meaning that this is required input. This is one of the key things I want you all to remember when you're doing global editing for either global pipe editing or you can do global junction editing. Is when you do global editing, this property window is only a template window. So that means that you only need to specify what you actually care about changing in that step, which in my case is simply material, size, type, and friction model. I don't care about the length right now. So I can leave this field completely blank if I want to. Now, one other thing I'm going to specify is I'm going to go to the optional tab, and I'm going to turn on the option to display the nominal size on the workspace, as well as the pipe number. So that's an additional thing I'm going to do with the optional window. Now I'll go back and I'm going to click OK. And this is the list of input parameters that you are going to change. So if you check the boxes for these parameters, those changes are going to be made. So if you just click on the all button to check all the boxes, it might be okay the first time, but I want you to pay close attention to what's going on here. Look at this. The length field is checked, but it's set to be unspecified. So if you already specified the pipe lengths and you keep that box checked, it's going to set them all back to unspecified. So you need to pay attention to what you're doing. So just for the sake of being careful, I'm going to uncheck that box. And I'm going to click Apply Selections and click OK. And now you can see that we have some pipe sizes. If you right-click and hold your right mouse button down, it'll display the input information in the inspection window. And as you can see, length is still unspecified. In addition, if you click on the Properties tab in the Quick Access panel, and then you select a pipe or a junction, it'll display your input information here as well. Also, if you already ran your model ahead of results, it would display output also. And so that's my pipe, my junction, my pump, my other pipe, etc. Now, I'm going to do another global editing operation for the pipe length this time, but I'm only going to do it for the first 3 pipes. So I'm going to select these 3 pipes right here. I'm going to go to Edit, Global Pipe Edit, and the neat thing is when you select them on the workspace, it's already going to check the boxes for you, or if you click the workspace button. So if I was to click on None and then Workspace, it gets all the pipes that are selected on the workspace. So that's handy. Now I'm going to click on Select Pipe Data, and this time I'm going to put in 25 feet for the length. You can change the units on the drop-down menu if you want, and I don't care about anything else. I'm just going to leave that as it is, because the only thing that I care about right now is my pipe length. So as you can see, global editing is a very powerful capability, and with great power comes great responsibility. So pay close attention to what you're doing. So now my first 3 pipes are specified. Let's take a look at the last one. This pipe right here is 1,000 feet long. And so this pipe in reality is traveling all over the place. It can be moving around all. That would be a really weird piping system for sure, but maybe it is. Well, I don't want to have to use a whole bunch of extra junctions just to model my minor losses and fittings whenever I have a directional change. There's a much easier way than having to use all those junctions to account for your minor losses. That is the beauty of the Fittings and Losses tab. So I'm going to click on the Fittings and Losses tab and then specify fittings and losses. And this is where I'm going to throw in some fittings here. So for elbows, I'm going to just click on the rows and put in some quantities here. There's 7 of these. There's 5 of these. And as you can see, whenever you click on the different row, the picture changes. And if you double click on the picture, that's going to tell you what reference that we're using for the loss model. I'm going to throw in a couple of valves and maybe a check valve. I don't care about modeling these explicitly as junctions. I just want to account for their losses themselves. So here I have a total K factor for all of these fittings of 17. I'm going to add an additional K factor of 15 just to account for any other potential fittings that I don't know about. So I'm going to add that additional K factor. What this does is it's going to calculate the pressure drop due to this total K factor. So we have our delta P equals your K factor times 1/2 rho V squared. And this delta P that's calculated based upon the K factor is going to be lumped in as an additional pressure drop onto the pipe on top of the dP from the Darcy-Weisbach equation. So this is a phenomenal way of being able to still account for all of these different minor losses by keeping your model simple. So the only thing that you're losing is the resolution of wherever these step changes occur, but you're still going to have the same overall pressure drop throughout your system. So this is a really good way to account for all of the accuracy and losses, but keeping your model simplified. So now I'll click OK. And the next thing on the optional tab that I want you all to be aware of is the other way that you can model elevations in a pipe. And so if you turn on this option right here to use intermediate elevations, this is where you can specify the elevation change of an entire pipeline with a single pipe. Now, I'm not going to demonstrate how to do this. I'm going to show you where you can find a blog article that I wrote that demonstrates it. So if you go back to our website, aft.com, under the Learning Center and then Tips and Tricks, I'm going to give you all a homework assignment. I want you to do a keyword search on the magnifying glasses for intermediate pipe elevations. And when you do that keyword search for intermediate pipe elevations, you're going to find this blog article that I wrote, and it will demonstrate exactly how you would be able to use that feature. So be sure to check it out. I think it's nice and informative. I'm not afraid to do a little shameless self-promotion of my blog articles. All right, I'm going to turn this guy off right now, and I'm going to click OK. The red ampersand means that you have fittings and losses inside that pipe. That's what the ampersand means. All right. Now, one thing that I forgot intentionally on purpose is, oh, there's supposed to be a real valve in that pipeline. It's a butterfly valve, and I forgot to draw it. So the question is, do you have to go through the painful process to select the pipe, break the connection, drag a valve on there, and throw in another pipe? Well, the answer is no. You don't have to do that. There's a much, much easier way. Now watch this. This is really cool. So in AFT Fathom 11, we included multi-level of undo. And so if I do Control Z, and Control Z, I can keep undoing any workspace change that I make. So that way I didn't have to delete all those stuff manually. I just hit Control Z. All right, so instead of breaking your connections, I'm going to hover over the valve junction. I'm going to hold the Shift key and click and drag the valve right on top of that pipe. And this is where I'm going to split the pipe, where I'll put the pipe 50 feet downstream of this process system, and I'm going to put the fittings onto the second pipe. And there we go. That way, I don't have to go in and break any connections. Makes it nice and easy for me. So this valve right here, again, not only does Fathom by default remember the most recently used pipe elevation, if you're doing a split like this and there's an elevation change, it will take that into account when you're splitting the pipe. So if that's not actually at 10 feet, then be sure that you change that. So this is going to use a handbook option for the K factor, and it's going to be a butterfly valve. All right, now let's turn off the list of undefined objects because that's all fully specified. And the numbering here drives me nuts. And so as you have added and deleted many pipes and junctions, it could throw off your numbering system. So if you go to the edit menu and then renumber, you can turn on the renumber wizard where you can use this to easily go about renumbering your system, and this gives you the instructions of how to do it. So all I'm going to do is just click on each junction. So I have 1, 2, 3, 4, 5, and then 6, and I'm done renumbering. So remember to do your renumbering after you've laid everything out and you want to get a better numbering scheme. Okay, so I have my system fully laid out, and I do have all green check marks and a green status light where I can run my model and generate my results. But I'm doing 3 things. I'm trying to size my pipes, because I don't know that 4 inches is what I need to use. That's just a guess. So this example problem that I'm demonstrating today is a pipe sizing, pump sizing, and supply tank sizing example all in one. So if you have a very, very simple system like this, where all you're dealing with is a single flow path, this is a poor man's way of how you would go about sizing your pipes. I draw my system once and I define it, and then I'm going to select everything on the workspace, and I'm going to go to edit and then duplicate special, and I'm going to offset the numbers by 100. That way I can see that pipe 101 corresponds with pipe 1. And then I'm going to duplicate special one more time. So here's why I'm doing this, is because I'm going to run 3 completely independent systems on the same workspace at the same time. But this system is going to be a different diameter. So I'm going to select those pipes in the workspace, go to edit, global pipe edit, and they're already checked off here. So this is going to use 5 inches in diameter. Now I know that 5 inches is a common size that you're going to use. I get it. But just go with it, because the idea right now is to show how you can quickly and easily try different pipe sizes. This system here is going to be 6 inches in diameter. So I'm going to do another global editing operation where I change this to 6 inches. And again, I'm only checking the box for the parameter I care about changing. And there we have it. So I've got my 4-inch, 5-inch, and 6-inch system. This is how I'm going to be able to determine which pipe size that I need. I have a velocity requirement where the velocities have to be less than 6 feet per second. So I'm going to go to the tools menu and turn on the design alerts. The design alerts are what you can use to flag your attention if a certain minimum or maximum value of something is exceeded. So I'm going to click on create new design alert and give it a name, 6 feet per second max velocity. Change the parameter. So this is going to be velocity. As you can see, there's tons of parameters available for you. And it's going to be maximum of 6 feet per second. It's going to apply to all the pipes in the workspace. I'm going to add the design alert. So what this is going to do is that if the velocity, if any of these pipes are larger or greater than 6 feet per second, I'm going to see big red warnings, and it's going to highlight those velocity violations in the output table. So this is what I'm using to help me size my pipes, is by duplicating the system as well as doing the design alerts for velocity. That's how I'm setting things up. All right. Now, the next thing is to set up my tank sizing. So again, the liquid surface elevation I specified for my tank of 10 feet is just a flat out guess. So I want to make sure that I have plenty of NPSH available for my pumps. But the thing is, I don't have a pump curve or a NPSH reference value. So I'm going to keep it a little bit more simplified. I want to make sure that every pump has a minimum of 5 psig in suction pressure at the pumps. So the way I'm going to do that is by changing the supply tank liquid height in order to ensure that I have 5 psig at the pump suction. Now imagine how challenging it would be to have to change every single reservoir one at a time, run your model, go and check results, and then repeat that process over and over, unless you're really, really, really good at guessing. That's where the GSC module is really helpful. So I'm going to click on add-on modules, goal seek and control, and I'm going to add on my goals and variables. So in the analysis menu, I'm going to go to the goal seek and control manager, and I'm going to choose new variable. And what am I going to vary? It's going to be the reservoir liquid level. And so now that I've defined that variable, I'm going to select the row and I'm going to duplicate it twice. And this is where offsetting the numbers by 100 is helpful, because I just need to go in and change the number. Junction 101, junction 201. And there we go. Now, how am I going to fix the supply tank liquid height? Well, with my goals. So I'm going to do new goal, and this is going to be a goal for pressure. I want to make sure that the pressure is equal to 5 psig at the outlet of pipe P2. So if we look at P2, that's right here, and then the outlet is the same as the pump suction. So that's what I need to be at 5 psig. So now that I've defined a goal, I'm going to select that row and duplicate it twice and simply change the number, 102 and 202. All right, and click OK. So I have a V and a G, meaning that I have a variable for this object and a goal for this object. So my goal seek and control checklist item is all completed. Now, before you run your model, it's always good to get a quick sanity check of your input. I showed you how to right-click and hold your mouse on a pipe or a junction to bring up the inspection window. The best way to evaluate your input is on the model data window. The model data window is a tabular format for all of your input information. There are 3 sections, a general, piping, and a junction section. You can collapse each section with the arrows. You can also resize the sections by clicking and dragging the borders up and down, just like so. And This is really powerful for being able to quickly scan down this list to make sure that you have unit consistencies, making sure that things are not off by huge orders of magnitude. And it's really easy to be able to spot mistakes when you are using the model data window. So I highly encourage you to get familiar with it because we use it all the time for troubleshooting models. Whenever there's a convergence issue, it's usually always because of input problems. So use the model data window to your advantage. It's not completely showing every single piping parameter that's available. If you go to the model data control button, this is where you can turn on additional parameters. So as you can see, I'm currently only displaying 13 out of 50 total piping parameters. And then there are also different parameters that you can change with the general components. And be sure that you check out these other tabs as well, because they allow some more flexibility for looking at your model data window. All right. Last thing I'm going to do is I'm going to pre-configure my output results. So this is the spreadsheet with the pen tool, which is the output control. And this is where you can define which results you want to look at in your output window. So here, these are all the results for the pipes. As you can see, I have 89 parameters that are available, but these are the ones that will be displayed in the output table. So you can customize this with more or less parameters. So I'm going to customize it a little bit. I'm going to remove several parameters that I don't care about, and I'm going to remove those. I'm going to scroll down and I'm going to add nominal size, move it all the way to the top. I'm going to rearrange my velocity as well. That way I can easily see which pipes are going to work and which pipes are not. And then I'm going to change the units to PSIG. And there we go. And then for my junctions, I'm going to add in my pressure loss. All right, perfect. So everything is all set up and I'm finally ready to run. And I'm going to click on run model and it's going to make me save. So I'm going to call this system sizing example. And that was nice and quick. Took less than a second for it to run. All right. The output window looks a lot like the model data window, where you have the same 3 sections of tabular results this time. You can expand and collapse each section just like you can with the model data window. So I'm going to collapse the junction results, and I'm going to make the text larger with the scaling tool here. So these are my design alerts that are telling me that the velocity is higher than the allowed value for these specific pipes. And then it's highlighting those violations in the output window. So this is, again, my poor man's way of sizing my system when you have a very, very simple single flow path. I can clearly see 4-inch and 5-inch are not going to work. I need to go with my 6-inch diameter system. And so a quick note is that if you do have a system that's more complicated than a single flow path, you're going to want to take a look at maybe using the automated network sizing module. That can help you size all of the pipes in your system in order to minimize your life cycle cost or your initial cost or your overall piping weight. And so it's a really powerful tool. All right, so 6 inches is the system I got to go with. Here are the various pump results. I can see for a 6-inch system, I need a pump that can deliver 245 feet of head, and I need about one that can deliver at least 32 horsepower or so. And then what are my resulting liquid levels for my tanks? Well, that's in my GSC variables. So here I can see that for a 6-inch diameter piping system, I need a supply liquid level of about 25 feet. So as long as I have a liquid level in my supply tank of 25 feet, then I should be able to achieve my goal pressure of 5 psig at the pump suction. So now my pipes are sized, my supply tank is sized, and now I'm going to find a pump curve that's going to meet this operating point. So this is where I'm going to introduce the scenario manager. So I'm going to click on this button right here. Let me circle it for you. It's the magical create a child button. Be careful how you use it. All right, so I'm going to click on create child, and I'm going to give it a name called pump curve. A very original name for sure. And in this particular scenario, my goal is to find a pump curve that meets this operating point. So now in this particular system, what I'm going to do is I want to take the results for these liquid levels and I want to convert them to input on my workspace. So I'm going to click on the thumbtack that says transfer results to initial guesses. That's going to transfer both the GSC variable data and the calculated results. So now I can see that I have exactly the liquid height that I need, right under 25 feet. So I don't need the 4-inch and 5-inch systems anymore. I'm going to delete them from the workspace. Now with the scenario manager, those piping systems are still there in the base scenario, but they're not in the pump curve scenario anymore. So one of the things I want you to remember is the green circle with the check mark in it. That means that this is currently the scenario that you are modifying. And so this is the only system I care about at this point. I can turn off my GSC because I already have my liquid height defined, and my model will run a little bit quicker now. And so now I'm going to find a pump curve that meets this operating point. The way that you do that is by clicking on the pump with a spark on it. And I'm going to use the internet. And so when you use the internet, we can work with IntelliQuip. IntelliQuip is a company out in Pennsylvania that works with over 30 pump vendors, and they have a internet pump selection capability, which is really powerful. Now, these are the only vendors that are not stingy. They list their pumps available here in this format without requiring a subscription to their online pump catalogs. So you can use these and bring the pump curves right into Fathom. So if there's other pump manufacturers that you're dealing with, contact IntelliQuip to be able to get in some other vendors here into this list. So I'm going to just keep it easy and use the first one. And you just go through the pump selection process where it takes your operating point from Fathom. And I'm going to select some product lines to figure out some pumps that'll work. And I'm going to sort everything by BEP proximity. And I'm going to use this pump right here because it's operating very close to 100% of BEP at my design flow rate of 500 gallons per minute. So this spec sheet information you can download in a PDF if you want, but what we need for Fathom is the IQX file. So I've downloaded the IQX file. I'm going to move it over to my desktop so it's easy for me to find. And now I go back into Fathom onto step 2 to open up that IQX file. And so this is where I'm going to choose to apply the data to the pump in my model. So now when I go back to the workspace and I open up my pump here, we can see that we've got our head curve, our MPSH curve, and efficiency curve. All right, this is amazing because I have some great data here. If you click on enter curve data, you can see all the raw data. Now, as you notice, we do not have data points for every single value. That's perfectly fine. Like I mentioned, you don't have to have hundreds of data points in order to generate an accurate pump curve. The reason why is because we're not using the data points for calculations. We are fitting the data points with a polynomial or an interpolated XY curve fit. So if you have a pump curve that looks like this, and maybe you have some data points that are kind of scattered, that's fine, because overall the curve is going to try and meet those data points as best it can, and this is still going to give you an accurate curve. So just read off a few good data points from your manufacturer curve and you're going to be just fine. But if you can find one on a tail clip, it does make it easier for you. Now, I'm going to turn on the preferred operating region in the configuration data tab, and you're going to see what impact this makes for me on my pump and system curve. So I'll click OK. All right. Now, before I run the model, I just want to mention really quick that it is at the top of the hour for the webinar. I'm going to keep going and give you guys all some bonus content. And so there's some important things I want to demonstrate that I want you to know. So if you're able to hang in there and stay on, great. And it'll be awesome to have you. If you need to head out, no problem. Thank you for listening in. And I hope that you have a wonderful rest of your week. You will be sent a recording of this webinar, and then just pick back up at about an hour into the webinar where I'm leaving off right here, and that way you'll be able to see the rest of the content at your leisure. So for those of you that are able to stay on, I'm going to keep going forward. For those of you that need to head out, thanks for listening in. Have a great day and rest of your week, and I'm going to keep going forward. So I just specified my pump curve. Now I'm going to run my model again. And when we look at the output window for the pump summary, we can see that our pump curve is doing an excellent job at meeting the original operating point. But now we know our pump is about 77% efficient, which is really good. And then we know our actual power draw, our BEP proximity, and our MPSH comparisons. So you have a lot more information when we're able to put in the pump curves in that fashion. Now, here's how we do our pump and system curve. If I go to the graph results window, the first time you go to the graph results window, you're going to see this thing right here, which is called our graph guide. If you click on this button, what would you like to do? That's what brings up the graph guide. So if you've never made a graph before, use the graph guide and this will walk you through the process. If you just want to do something quick and simple, I'm going to click on quick and simple and do a pump and system curve. And as you can see, it's already got some predefined parameters for me. So the only thing I need to do is just click generate. So let's do that. So I'm going to click on generate, and there's my pump and system curve. Now, I don't like how it doesn't go out very much further. So I want to expand my flow rate range using a user specified input. So what I'm going to do is I'm going to modify this a little bit. I'm going to click on user specified, and I'm going to expand my flow rate range out to 800 gallons per minute. I'm going to show my efficiency curve, and now I'm going to regenerate the curve fit. And there we go. So now this takes my pump and system curves out a little bit farther, and this is why I turned on the preferred operating region, is so that it will put the X's for the 70% of BEP lower bound and the 120% of BEP higher bound. So I want to make sure that the curves are intersecting as close to the BEP as possible, but certainly within these two X's. So that's really helpful with turning on the preferred operating region. Now, this is a common graph that I'm going to turn back to periodically. I don't want to have to reset these parameters every single time. So what I'm going to do is I'm going to click on the folder with the blue plus sign on it, and that's going to file this graph away into the graph list manager, which, as you can see, I've got a graph folder. It's a really convenient filing system for the different types of graphs that I want to look at. So I'm going to give this a real original name, pump and system curve. So now we can see that I have one graph in my graph list manager. Now we have a single graph folder. You can create multiple graph folders if you want. That way you can have a really sophisticated filing system for all your graphs. I would typically demonstrate how to do a profile plot, and I'll go ahead and do it here just for the sake of doing a profile plot. So I'm going to click on the green plus sign, and I'm going to choose profile, and I'm going to select all the pipes, and I want to look at the pressure profile in PSIA. So if I click on generate, bam, there it is. Now, if I click on this blue square, this is going to show me where my junctions are located in that graph. But suppose that I want to be able to see my pressure in terms of PSIA units and maybe a different set of units. This is where you can add on an additional parameter where it would be the same one, pressure static, but this time I'm going to use PSIG. And with this row, I'm going to click on the blue arrow that points to the right to make it a secondary y-axis. So now, as you can see, I have a single line that represents the static pressure with PSIA units on the left and PSIG units on the right. So this is the same parameter, different units on the secondary y-axis. Let's make it a little bit more exciting. Let's show the hydraulic grade line on there. So I'm going to add on another parameter, actually another two parameters. This one is going to be hydraulic grade line, and then the fourth one is going to be elevation. And the elevation I'm going to move over as a secondary y-axis. So here's what's going to happen when we have these two graphs above and then these two graphs below. It's going to create what we call a stacked graph. So when you have this type of situation, we will have our pressure profile on the top and then our hydraulic grade line and elevation profile on the bottom when they share a common x-axis. So this gives you a lot of information here. So now I'm going to click on the blue folder again. I'm going to call this P and HGL and elevation versus L. So this is why I file away these graph list items, because if I go in and I make a change to my workspace, I rerun my model, I don't want to have to reset those parameters every time. Just double click on the graph list item and that regenerates your plot immediately. Or another useful way to do it is you can right click on the folder itself and load both of the folder items in the same tab. Very cool. All right, last tab here is the visual report. So this is where you can specify your parameters to display right on top of the model itself. So I'm going to display some pump information, percent of BEP, flow rate and head rise. I'm going to show my CV, K factor, and pressure drop for the valve. I'm going to show my liquid surface elevation and my surface pressure. I'm going to change my units. My font size. And voila. So here I'm showing the units in a legend. That way it declutters the visual report. And this is amazing because it's an outstanding way of being able to show your results right on top of the model itself. This makes it really easy for people to be able to follow along with what's happening in your system while if they don't have a good understanding of what the system is doing, perhaps. Maybe they don't know the system and you're trying to show them what it does. So be sure to use the visual report. It's a really helpful tool. All right, now last thing I want to demonstrate today is how to do multi-scenario pump and system curves. So I specified a normal operating scenario where my liquid height is about 25 feet for my supply reservoir. What if we have a situation where my liquid level is much lower and my discharge reservoir is much higher, which increases the system's static head? Also, what if I want to model my pump operating at different speeds? How do we do that? Well, that's our scenario manager. So what I'm going to do is demonstrate some scenario manager capability by creating another scenario called normal liquid supply. And then I'm going to create 3 children within that parent. So this will be called 100% speed. And then I'm going to select that parent again, 95% speed. And 90% speed. So what I'm going to do is in the second scenario, I'm going to load the 95% speed scenario, and I'm going to go into the pump window, and on the variable speed tab, it's going to be changed to 95% speed. I did not need to change it in this scenario because it already was 100. So I only needed to change it here and here. So I change it and I click OK. And then I'm going to change it in the 90% speed scenario as well. Now this, you may not know what speed you need to operate at. Instead, you might know that instead of 500 gallons per minute, you only need 400 gallons per minute. That's where you can do a controlled pump set point. So when you specify your set point, Fathom will adjust the pump curve for you via the affinity laws, and it'll calculate what speed that the pump needs to operate at in order to give you that controlled set point. So keep that in mind when you're modeling variable speed drives for your pumps. Now, I have this family of scenarios. Just like you have the magical create a child button, you can create children, you can delete children, you can also clone children, and you can clone entire families of scenarios. So what I'm going to do is I'm going to right click on the parent. I'm going to say clone with children. There might be some families that you don't want to clone for sure. This is going to be called low supply and high discharge. So I just cloned the entire family, and now the only change I'm going to make is to the reservoirs. This reservoir is going to be at a 5-foot liquid surface elevation, while this discharge reservoir is going to be at a 215-foot liquid surface elevation. Now, here's the beautiful thing, is that when I make this change in this parent scenario, it propagates down to each of the individual speed scenarios. So I only need to make the change once, and then it's changed for all of these. How can I be sure? Well, that's where you can right-click on a scenario and open up the scenario comparison tool. So this is where you would choose which scenarios you want to compare with each other. So those are the 6 scenarios I'm going to compare. And yes, I want to highlight unique values. That way, if anything changes, then it'll show me a different color. I am going to do a fully exhaustive comparison of all potential parameters that are available so I can know if anything changed. You can also see if you change your solution tolerances or your system properties in any scenario, because you can. You can change any parameter in any scenario that you want. And then lastly, I'm going to compare all my pipes and junctions. And so now we show the comparison. So this is already filtering for me to only show the pipes or junctions that have differences and only show me which parameters are actually different. So as you can see here, for pipes, There are no differences at all. No differences in solution control or system properties. The only things that are different is my supply tank, my pump, and my discharge reservoir. And the only parameter that has changed is liquid elevation, speed, and liquid elevation. So here's my first three scenarios. I can see that I have the same original liquid surface elevation, but my pump speed is changed accordingly, just like how I wanted it to be set up. If I scroll further over to the right, I can see that I have my new liquid surface level, and I've got the same 3 pump speeds. So everything is good to go. I just verified that I set up all my scenarios correctly. Now I'm ready to do a batch run. So this is where the magic happens. I'm going to click on File and then Start Batch Run, and I'm going to add those 6 scenarios to the list. This is why I created that pump and system curve graph list item, because I want to click this button here to create a multiple pump versus system curve using the pump and system curve graph list item as a template that I created. So basically just click this and then we'll start the run. So this goes through, it runs each scenario. After it runs that scenario, it generates the pump and system curve for that particular scenario. And it does it pretty quickly. And so it's flying through those scenarios right now. You can run 100 scenarios if you want. Go grab a cup of coffee and then come back and you'll be able to look at your results. And so it's got one more scenario that it has to run. And now I have my message that tells me that I have all batch runs completed without errors. Perfect. So you can look at any of the results in any of these scenarios. And I'm going to go to the Graph Results tab. And so right here, this is the new folder that it created for me automatically when I did a batch run. And basically, it used this graph list item template to create individual graph list items for each scenario. But all you need to do is right-click on the new folder, click on Load Multiple Scenario Graph, and if I was to just click Generate, it's going to show insanity on the legend. So this has everything. Let's clean this up a little bit. So instead, I'm going to turn off something. So I have my pump curve for 100% speed, 95%, and 90. So I can turn it off in these other scenarios because it's the same. Next, I need to keep my system curve for only 2 of the scenarios. So I can turn it off here and here. And then lastly, I need my POR and my efficiency curve, so I can turn them off in these cases as well. And that way it simplifies the legend. And bam, there it is. Isn't that beautiful? You have your 2 system curves where the static head increased because of the liquid elevation changes. We have all 3 pump speeds. We have our efficiency curves and the preferred operating region for each pump operating point. So this gives you a lot of information where you can show all of your different scenarios and your pump and system curves together. You could click on this button right here, which will copy the XY data into Excel for you, or it'll copy it so you can paste it into Excel, but there's no need. Just click on this button right here, and that's where you can copy the image itself, and you can simply go right into PowerPoint and simply paste it right into your reports. There you go, just like that. So you don't have to do any extra Excel work. All of this pump and system curve stuff can be done right in Fathom, as long as you're using AFT Fathom 11. So this was a new feature that came out with Fathom 11 that I'm personally really excited about, and this is how you do it. All right, well, we covered a lot of ground today, and I want to thank you all for your time, and hopefully this just goes to show how you can very quickly take a really simple system and accomplish a lot with it, with many different scenarios. I didn't even show how you can easily split the pipes upstream and downstream of the pump in order to do a pump in parallel. You know, maybe you have an expansion to another system. And if you use those features like global editing and design alerts and the goal seeking control module and scenario manager and graphing, it's going to be able to take your flow modeling capabilities to a whole new level, and it's going to dramatically streamline your efforts. So if you have any questions, feel free to contact us. You can contact me. I'm Ben Keiser at AFT.com. That is BenKeiser at AFT.com. I'll use the annotation manager for this. And so if you want to do a note on your workspace, there we go. So there's my email address for you. So if you have any questions or if there's any other topics that you want to see, email me and I'll be happy to demonstrate that for you. Thank you very much, everyone. Take care and have a wonderful week. And I enjoy you guys listening in. Thanks, everyone.